what really happened when the Earth completely froze over. Dear traveler, greetings. Today, we uncover a little-known Earth, frozen in a white silence, slumbering beneath a thickness of ice that engulfs seas, mountains, and continents. A world of pale light, where the ocean is sealed under kilometers or miles of ice, and where the very breath of the planet seems suspended. For it is in this long, glacial night that the future is forged, where life retreats, adapts, and waits for its moment to rewrite history. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel to not miss anything. Thank you, and have a nice trip. We are immersed in a distant era, about 830 million years ago, where Earth undergoes great geological metamorphoses. At this time, a massive continent called Rodinia dominates the Earth's surface, but this supercontinent is slowly starting to fracture. Under the effect of internal forces and the movements of the Earth's mantle, the plates are gradually moving away from each other. Deep fissures appear, paving the way for the formation of new oceans and the progressive drift of continental blocks, which then embark on their journey to different regions of the globe. The separation of the continents accelerates, disrupting the configuration of the lands and the circulation of the oceans. At this time, most continents are near the equator, which strongly influences the climate. Unlike vast polar ice caps that reflect light, tropical surfaces absorb more solar energy. The result, the lands heat more intensely, in turn, warming the atmosphere and surrounding oceans. This concentration of heat in tropical regions marks a major turning point in the planet's climatic evolution. The tropical position of the continents not only influences the temperature, it also changes the winds, ocean currents, and primitive ecosystems. Multicellular life forms are not yet present or just barely emerging. However, the oceans are full of unicellular microorganisms such as cyanobacteria, which colonize shallow waters. These tiny beings, at the base of the food chain, gradually release oxygen into the atmosphere. Although this rate remains low compared to today, it already transforms the chemistry of the oceans and sets the stage for the evolution of complex life. In parallel, the fragmentation of Rodinia leads to the formation of marginal seas, more confined, with varied environmental conditions. These marine environments house a microscopic fauna capable of adapting to waters rich in minerals or variations in salinity. As for the flora, it is mainly composed of microscopic algae, sometimes forming vast expanses on shallow seafloors. These structures, called microbial mats, leave characteristic traces in sediments named stromatolites. These formations are valuable to researchers because they reveal interactions between life and the geological environment at a key stage in Earth's history. At the same time, the Earth experiences eustatic fluctuations, which are changes in sea levels. These oscillations result from several factors, such as plate tectonics or changes in the volume of water in ocean basins. The slow movements of the crust influenced by the mantle change the shape of the sea floors and cause marine transgressions, advances or retreats of the sea on continents. In this dynamic context, the first signs of global cooling appear. During the Tonian, carbonate rocks, such as limestones and dolomites, record a progressive decrease in global temperatures. The carbonates formed during the Tonian, resulting from the precipitation of minerals in marine waters, reveal subtle variations in isotopic ratios. By analyzing the composition of carbon and oxygen, scientists deduced that an increasing proportion of colder waters circulated on the globe's surface. Some geological sections even show signs of localized glacial events, suggesting that ice might have begun to form, initially in the most remote polar regions. These geochemical indices show that the Earth's climate, until then relatively mild, is beginning to change. Although the atmosphere is still rich in greenhouse gases, notably carbon dioxide of volcanic origin, its concentration seems to be already decreasing. This decline could be explained by more intense chemical weathering of silicate rocks near the equator, a natural process that captures and transfers this gas to the oceans as carbonate sediments. During this Neoproterozoic period, the Earth oscillates between tropical heat and the onset of an ice age. Indicators present in the rocks, such as the Tonian carbonates, reveal the gradual shift from a stable climate to increasing instability. This evolution will lead, a few tens of millions of years later, to unprecedented global glaciations. But for now, only a hint of cool air is felt, while the tropical continents of Rodinia continue their slow dispersion, sketching a map of the future. Just before the Great Sturtian Glaciation, the world had a completely different face. The continents, resulting from the fragmentation of an ancient supercontinent, were grouped around the equator or subtropical areas. The tectonic activity was in full transformation, with the formation of new ocean basins and a reorganization of deep marine currents. Around the dispersed continental blocks, vast expanses of water favored complex interactions between lithosphere masses. These dynamics profoundly influenced the distribution of heat on the globe's surface, contributing to the emergence of the first polar ice of the Neoproterozoic. In the background, the Moravia Ocean and the Adamastor Basin were part of the new so-called marginal seas, born from tectonic movements. Unlike today's great oceans, these basins formed at the border of continental blocks, undergoing separation. Moravia illustrated the vast expanse of water surrounding the equatorial lands of the time. As for the Adamastor Basin, linked to Africa and South America, it was opening in another area, adding new marine passages. As they expanded, these spaces changed the global geography, promoting exchanges of water, heat, and nutrients. In these ancient oceans, marine life was still dominated by microorganisms, such as simple algae and bacterial colonies. Fossils of complex animals are absent because the great explosion of biodiversity had not yet occurred. Yet these small forms of life already played an essential role in the cycle of elements. Through their metabolism, they altered the chemical composition of the water by releasing or absorbing certain molecules. Thus, any change in temperature or marine current could profoundly affect these microscopic communities. Before the Sturtian glaciation, warm currents circulated mainly around the equator, diffusing heat to the poles. This global movement, called meridional circulation, depended on the Earth's rotation, winds, and the position of the continents. The opening of the Moravia and Adamastor oceans created new passages, modifying the thermal distribution of the waters. Subtropical gyres then formed. Tropical gyres are immense ocean vortices that transported warm or temperate water in loops. These slowly rotating currents, centered around areas of high pressure, played a key role in the thermal balance of the planet. These subtropical gyres deeply altered the oceanic dynamics. They maintained warmer surface zones, while others, less well-supplied, began to cool. In this still tropical climate, most of the solar energy remained concentrated around the equator, though the brightness was lower than today. But as the continents drifted apart and the seas infiltrated them, the distribution of heat changed. Some regions warmed up, others cooled down, creating a new thermal equilibrium on a planetary scale. One of the major effects of this oceanic reorganization is the decrease in heat transport to the poles. Before the opening of the Moravia and Adamastor oceans, equatorial heat circulated more freely, due to the lack of significant continental barriers. With the new tectonic configuration, some pathways have widened, others partially blocked, disrupting global thermal diffusion. As a result, less heat reached the high latitudes. On the scale of geological time, even a slight modification of these transfers can trigger major climatic upheavals. At that time, Earth did not yet have large polar ice caps like it does today. Ice existed occasionally, but in localized or seasonal forms. A stable ice cap at the North or South Pole was still absent. For immense glaciers to form, a much more marked drop in temperatures was necessary. However, with the slowdown of heat transport to the poles, cold air began to settle there permanently, making the appearance of permanent ice more likely. The gradual establishment of polar ice was likely aided by several mechanisms. First, the new distribution of continents, surrounded by marginal seas, isolated certain regional currents. Then, a portion of tropical heat no longer effectively reached the poles, allowing surface water and air to cool further. Finally, microscopic biological activity, although difficult to trace, could have captured certain oceanic gases, thereby altering climatic balances and reinforcing cooling. Even before the full establishment of the Sturtian era, tectonic dynamics and the breakup of supercontinents were already laying the groundwork for change. The retreat of heat transport to the poles, accentuated by subtropical gyres, played a key role in the appearance of the first ice. This slow process was soon to intensify, plunging Earth into global cooling. Vast ice sheets would eventually cover continents, marking the geological history with an unprecedented glacial imprint. During the Neoproterozoic, between 1 billion and 540 million years ago, Earth's atmosphere contained a fragile balance of greenhouse gases, including carbon dioxide. Its concentration was estimated between 0.01 and 0.02 bar, a level much higher than today's. This gas played a crucial role in maintaining heat at the surface. By comparison, the current concentration, although increasing since the industrial era, remains well below these ancient values. Carbon dioxide comes from many natural processes, such as respiration or decomposition. But in this distant time, intense volcanic and tectonic activity dominated. Fissures in the Earth's crust released magmatic plumes, forming vast basaltic flows on the surface. These eruptions also released significant amounts of sulfur dioxide, a major volcanic gas. By forming sulfate aerosols, these particles reflected part of solar radiation, thus contributing to cooling the planet. While CO2 increased, this mechanism occasionally countered the heat received at the surface. At that time, the oceans contained methane in high concentration, which influenced the climate. This gas, much more potent than carbon dioxide in the short term, came from the degradation of organic matter in anoxic, or oxygen-free environments. Specialized microorganisms, such as certain bacteria and archaea, thrived in these primitive conditions. Although complex fauna and flora did not yet exist, immense microbial communities covered the ocean floors and shores. They produced these gases while forming a fundamental ecosystem for life on a still hostile Earth. This period cannot be understood without mentioning the decrease in ultramafic mantle degassing. These magnesium and iron-rich rocks, originating from Earth's depths, once more frequently reached the surface. But with the evolution of oceanic spreading zones, this flux decreased. Fewer ultramafic rocks also meant fewer reducing elements released, such as free hydrogen. These gases played a key role in atmospheric chemistry, promoting methane formation. Their scarcity thus contributed to altering the planet's climatic and chemical balance. The balance of greenhouse gases played a crucial role in the survival and evolution of the earliest organisms. In the rare coastal zones where primitive algae appeared, the presence of carbon dioxide and the heat it retained were essential. Furthermore, the seawater in contact with the atmosphere saw its composition altered by the runoff of nutrients from volcanic coasts. This mixture favored the proliferation of photosynthetic microorganisms, which formed the base of future complex ecosystems. The exchanges between the atmosphere and the ocean, linked to the solubility of gases in water, also depended on the global temperature. This was already influenced by the position of the continents, mostly located in tropical areas. These lands, with their low albedo and their ability to reflect light, absorbed more heat than an icy surface. In this context, the concentration of carbon dioxide became a crucial factor. Too little, and the planet risked a sudden cooling. Too much, and the heat persisted. Fortunately, sulfur dioxide and aerosols sometimes helped restore a temporary balance. Here we are projected approximately 720 million years, or 448 million miles back, to a time when the Earth and the Sun were significantly different from what we know today. Solar luminosity was then about 6% lower, a decrease that, although it seems minor, was enough to influence the global climate balance. To understand the impact of this dimmed light on the planet's fate, let's explore the great astronomical mechanisms that modulate the climate over very long periods. When we talk about cyclical climate variations related to astronomy, we refer to the Milankovitch cycles. This concept, named after mathematician Milutin Milankovitch, encompasses several orbital phenomena that influence the sunlight received by the Earth. The distance between the Earth and the Sun, the tilt of its axis, and the shape of its orbit slowly change over time. These oscillations, over tens or hundreds of thousands of years, alter how solar energy is distributed between the poles and the equator. "20 million years ago, the position of the continents amplified the impact of the Milankovitch cycles. At that time, most emergent lands were concentrated around the equator in areas very sensitive to seasonal variations. This distribution influenced the albedo. Warm seas, coasts, and plateaus accentuated climate contrasts. Thus, even slight drops in global temperature could lead to ice formation on tropical plateaus, while warmer periods caused rapid melting. As a result, the global climate reacted strongly to even the slightest variations in sunlight. To understand better, let's focus on two key elements of the Milankovitch cycles: precession and obliquity. Precession corresponds to the slow rotation of the Earth's axis, a circular movement that lasts about 26,000 years. This phenomenon modifies the orientation of the Earth relative to the Sun, leading to seasonal variations in sunlight between the hemispheres. Thus, one hemisphere may receive more light in summer, directly influencing the melting or accumulation of ice. In an Earth dominated by equatorial continents, this effect could intensify snow accumulation or freezing in certain sensitive areas. Obliquity refers to the tilt of the Earth's axis relative to its orbit. The greater this tilt, the more marked the seasons, especially at high latitudes. Conversely, a lower obliquity softens the contrasts with cooler summers and milder winters. At this time, this tilt varied according to cycles of more than 40,000 years. With each change, the extent of the ice caps could evolve significantly, advancing or receding depending on the induced climate. During a phase of strong tilt, a very hot summer could melt some of the ice, before a harsh winter favored their return. Repeated over several cycles, these contrasts could lead to a progressive cooling, especially if the low solar luminosity persisted over several millennia. These astronomical variations interact in a complex play, but one essential point remains. The concentration of continents under the tropics amplified these effects. When a region transitions from a warm and humid season to a cooler period, its albedo changes, as does the amount of water vapor released. If equatorial zones become snow-covered, more light is reflected into space, accentuating the cooling. Conversely, a rapid warming causes the snow to melt, releases more liquid water, increases evaporation, and promotes cloud formation, triggering climatic feedback loops. During the Tonian era, between 850 and 740 million years ago, the climate archives reveal a profound upheaval of the Earth's system. To understand it, researchers rely on the analysis of carbon isotopes, particularly delta-13C. This parameter measures the proportion of carbon-13 relative to the more common carbon-12. It is expressed in per mil, present 0, and allows for the detection of very slight changes in chemical composition. However, during the Tonian, negative peaks around 5% 0 were observed, indicating a notable depletion in carbon-13. These negative peaks are often interpreted as a sign of a weakening biological pump. Normally, marine organisms like plankton or algae preferentially absorb carbon-12 during photosynthesis, leaving more carbon-13 in the water. This activity creates an isotopic signature detectable in the sediments, but if photosynthesis slows down, this difference diminishes. The proportion of carbon-13 then remains more stable, which results in a decrease in delta-13C. The decrease in biological activity could be explained by environmental changes, such as a lack of nutrients, a drop in temperature, or less abundant light. During the Tonian, strong variations in carbon dioxide and other gases probably disrupted the climate and the balance of marine ecosystems. The negative peaks of delta-13C then appear as real warning signals, announcing the upcoming global cooling. In addition to carbon variations, glacial marine deposits beyond 60 degrees latitude, approximately 66 degrees in imperial, are observed at this time. These are areas where glaciers or continental ice caps advance to the ocean, releasing icebergs. As they melt, these icebergs release the sediments they contained, which then deposit on the sea floor. These glacial traces, found in places, are said to be discontinuous because they are neither constant over time nor uniformly distributed. This shows that Tonian glaciations were not yet global, but were enough to form coastal glaciers up to high latitudes. Other geological clues reinforce the idea of a glacial climate. In pelagites, deep sediments, large rocks called drop stones or fallen stones are sometimes found. These blocks, occasionally found at the bottom of oceans, far from any terrestrial source, are too massive to have been transported by currents. The most probable explanation is icebergs that carried them from the continents. As they melted, they released these stones, which fell directly onto the seabed. Result: in the midst of fine muds, isolated fragments appear, proof of glacial transport, even moderate, in an environment once calm. These clues confirm that during the Tonian, the Earth was entering a cooling phase. It all begins about 717 million years ago, on a young and already very active Earth. At this time, volcanic arcs form where tectonic plates meet, giving birth to new island chains. At the heart of these volcanic reliefs begins a crucial process for the climate: large-scale silicate weathering. Imagine freshly formed mountains, hardened lava flows, beaten by abundant rains. Water infiltrates these silicate-rich rocks and triggers chemical reactions. By combining with carbon dioxide, these reactions gradually trap this gas in new minerals, contributing to the progressive decline of atmospheric CO2. In the atmosphere, carbon dioxide acts as a powerful greenhouse gas, trapping some of the solar heat. However, silicate weathering, continuing over hundreds of thousands of years, gradually reduces its concentration. This decrease weakens the atmosphere's ability to trap heat, causing a slow global cooling. Of course, no one can witness this, but this subtle change is enough to trigger a major transformation in Earth's climate. Near the equator, heat and humidity have always fueled the intertropical convergence zone, a region of heavy rainfall created by evaporation and converging winds. This system normally maintains a stable climate in low latitudes, but when carbon dioxide drops and the planet cools, everything goes awry. Less heat means less evaporation, which weakens the formation of tropical clouds. Gradually, the rain belt retracts, then collapses. Precipitations become irregular, humidity decreases, and cooling intensifies throughout the equatorial zone. During these cooling phases, the global average temperature drops below zero. This shift is not immediate, but remains rapid on a geological scale. Glaciers begin to form at the poles and on high elevations, gradually expanding each cold season. Initially confined to high latitudes, these glaciers seem to have no effect on the tropics. Yet, their influence will soon spread, deeply altering the climatic balance of lower regions. The process accelerates. Snow and ice, being highly reflective, send a large portion of the solar radiation back into space. This is called albedo. Frozen surfaces have a very high albedo, much more than the dark oceans or forests. The more the ice spreads, the more the Earth reflects light and the more it cools. It's a feedback loop. The ice increases the albedo, and the albedo intensifies the ice. Gradually, the continental ice caps leave high latitudes, advancing into unexpected areas, reaching up to about 30 degrees latitude, both north and south. To grasp the extent of this glacial advance, imagine the ice extending much closer to the equator than during recent glaciations. 30 degrees of latitude, now associated with desert or subtropical zones, then become frozen under extreme cold. The landscapes become vast fields of hard, shimmering ice. Rivers and lakes freeze over thousands of kilometers or miles, making life increasingly difficult for organisms that depended on a warm and humid climate. The fauna and flora, still very simple at this time, must face unprecedented environmental stress. Life is mostly limited to microbial forms, sometimes adapted to extreme environments such as underwater hydrothermal vents. In lowlands, the disappearance of liquid water and plant cover makes survival nearly impossible. Only a few areas spared by ice still offer refuges to these primitive life forms. As the ice caps expand, carbon dioxide continues to fall. Rainfalls, increasingly rare, dry out the soils and lift more mineral dust. Chemical erosion, especially on volcanic and sedimentary rocks, captures even more CO2. The volcanoes, though a source of this gas, no longer suffice to balance the cycle. The Earth then sinks further into a glacial climate. As cooling progresses, the Earth takes on the appearance of a gigantic intercontinental ice sheet, even though not all seas are yet frozen. The transition is stark. Coastal ice sheets and plateau glaciers extend over thousands of kilometers or miles, gradually covering livable lands. In a few million years, this ice transforms landscapes, traps water in immense frozen reservoirs, and causes a spectacular drop in sea levels. At the heart of this distant era, a decisive mechanism sets in, the albedo ice feedback loop. The more the ice extends, the more it reflects the sun's energy into space, accentuating the cooling. Conversely, the ice-free ocean, darker, absorbs heat. But as soon as it is covered with bright ice, this ability diminishes, and the cooling spirals out of control. The ice pack slowly advances toward the equator, driven by global cooling. As it reaches warmer latitudes, its reflective power strengthens the drop in temperatures. The more the ice spreads, the more the ocean loses its ability to absorb heat, and the more the Earth's surface cools. Solar rays are sent back into space, preventing any warming. Deprived of energy, the waters continue to freeze, amplifying planetary glaciation. With the expansion of the ice, the ocean's surface temperature drops by about 10 degrees Celsius, or 18 degrees Fahrenheit. This cooling strengthens the formation of sea ice and makes the environment increasingly hostile to sensitive life forms. Marine organisms, such as the first plankton, face tremendous pressure. Colder water slows vertical circulation, reducing the intake of nutrients. Under the ice, conditions become difficult, threatening the survival of many species. But the impact goes beyond the ocean. The immense ice cover traps atmospheric moisture. With less liquid water exposed to the air and an increase in cold, water vapor becomes scarce. The freezing air can hold only a small amount, which limits cloud formation and precipitation. The little remaining vapor freezes or is trapped in the ice caps. Result: the atmosphere dries out, and drought intensifies globally. Deprived of moisture, the Earth enters a true cryogenic desertification. The natural water cycle, consisting of evaporation and rain, collapses. The continents, frozen and dry, receive almost no precipitation. Rivers disappear, aquifers run dry, and the few areas that housed microbial colonies become uninhabitable. This icy drought does not affect just a single region, but the entirety of the emergent lands, transforming the planet into a uniform, arid, and frozen world. Terrestrial life, already scarce, faces even more hostile conditions. The few surviving organisms must flee or adapt to a world nearly devoid of water and nutrients. At the seaside, marine fauna and photosynthetic life forms attempt to subsist where the ice has not covered everything. Yet, the drop in temperatures and light cause biological productivity to collapse. Food chains waver, putting all species under increasing pressure. Over time, the ice gains ground in an unyielding cycle. The more it expands, the more the Earth reflects sunlight and the less it retains heat. The oceans freeze, the atmosphere stays dry, and most habitats disappear. The ice pack imposes its rule, a frozen world where warmth no longer finds its place. Imagine an immense ocean slowly freezing under a mantle of ice. The cold intensifies day by day, transforming the surface into a white and compact expanse. In some tropical regions, the thickness of the ice pack reaches up to 2 kilometers or 1.24 miles. Today, it seems unthinkable to see a frozen ocean near the equator, yet geological records prove that it did indeed happen. As soon as a thin layer of ice appears, it begins to reflect the sun's rays far more than a dark water surface. This light sent back into space prevents the planet from warming, amplifying the cold even more. Gradually, the ice pack thickens and expands, covering vast oceanic areas. Below, the heat can no longer escape, trapped under this frozen barrier, and the ambient air becomes increasingly frigid. In this frozen world, life must adapt to extreme conditions. Most marine organisms are then microscopic, without the complex mechanisms of modern species. Algae and bacteria survive by slipping into the rare cracks in the ice, where a few rays of light still manage to filter through. Clinging to thin films of liquid water, they continue to live and interact. Despite the cold, these micro-ecosystems remain active, driven by chemical reactions that we are only beginning to understand. Under this thick layer of ice, sometimes 1 to 2 kilometers, 0.6 to 1.2 miles, deep even in the tropics, the oceans retain some of their heat but remain cut off from the outside world. Yet, the seabed remains active. There, geological phenomena trigger hot water upsurges. These are hydrothermal flows. Magma, rising from the depths of the Earth, heats the water, pushes it to circulate through the rocks, and then ejects it in scalding jets through chimneys called hydrothermal vents. In this frozen world, these heat sources become vital. They support microbial colonies that, sheltered from the surface, continue their existence in darkness. In some areas, the hydrothermal flows are powerful enough to create small pockets of liquid water under the ice. These oases, although rare and often temporary, offer a respite in this frozen world. The warm water rises, remains liquid, and forms a protected niche. There, microorganisms settle, exploiting the heat from the magma and the dissolved minerals to survive. This way of life relies on chemosynthesis, a process where energy comes not from the sun, but from chemical reactions. In total darkness, bacteria transform iron or sulfur into organic matter. Despite the extreme cold, life persists in one of the most hostile environments on the planet. Under the thick ice sheet, the pressures are colossal. Kilometers of ice crush the masses of water in the ocean floor. This immense weight gradually deforms the Earth's crust, especially where tectonic weaknesses already exist. In this icy silence, thousands of meters below the surface, fractures begin to open. These are subglacial rifts. A rift is a fault, a tear in the Earth's crust, often linked to volcanic activity. Here, in the absolute darkness of a frozen ocean, the crust stretches, cracks, and magma begins to rise, slowly, through these invisible breaches. Even under kilometers of ice, these rifts create cavities where seawater seeps in. Touching the magma, it warms up, becomes laden with minerals, and gives birth to small isolated basins carved by the fractures in the crust. The wider the fissures grow, the larger these refuges become. In these hidden pockets, life organizes around another source of energy, the Earth's heat. There, microbes survive in an extreme environment without light, with stifling heat in some places, crushing pressure, and almost no oxygen. An underground world with no equivalent on our Earth today. In these deep fractures, true lava lakes sometimes form, called basaltic lakes. Born from dark lava, rich in iron and magnesium, these simmering reservoirs remain trapped under the ice. Under the colossal pressure of the ice sheet, volcanic heat maintains a thin zone of liquid water, a fragile barrier against total freezing. But this calm is deceptive. As the steam accumulates, the pressure rises. And if it were to be released, an explosion could disrupt the balance of this frozen world. Gradually, a truth emerges. Even covered in a thick ice shell, the Earth does not extinguish. Under the frozen tropics, tectonic forces continue their work. Hidden basaltic lakes, pockets of warm water, and subglacial rifts offer refuge to life. In these secret worlds, microbes cling to the warmth, to the minerals, to hope. for even plunged in a planetary winter, the Earth still breathes. At the heart of this icy desert, the oceans are imprisoned under a thick casing of ice, almost totally isolated from the atmosphere. In these dark abysses, a key phenomenon sets in. The conditions become anoxic. Normally, air and light allow the oxygenation of the waters, nourishing plankton photosynthesis. But under the ice, no more light, no more gas exchange. Photosynthesis collapses. Oxygen disappears. In this chemical silence, unstable compounds accumulate. The water becomes reactive, laden with elements on standby, ready to tip at the slightest change. A world where what geochemists call an extreme redox environment reigns. In this oxygen-deprived universe, some key elements change their behavior radically. Iron and manganese, for example, no longer have anything in common with what they are in a well-oxygenated ocean. Ordinarily, they react with oxygen to form solid particles that slowly settle on the seabed. But here, in these anoxic waters, there is no more oxygen to provoke their transformation. Iron and manganese remain dissolved, in a form known as divalent, which is much more mobile. They then accumulate in the depths, suspended in this dark and stagnant water column. A simple change in temperature or chemistry can sometimes cause them to suddenly precipitate or to be released, altering the fragile balance of this frozen ocean. Imagine a vast water basin, trapped under kilometers or miles of ice. At the surface, the ice-cold water, pore and gas exchanges, remains frozen, while in the depths, rare currents from hydrothermal sources diffuse some heat, and sometimes a breath of oxygen. These upwellings, although discrete, disrupt the balance. Where they appear, they trigger the oxidation of dissolved iron and manganese. In a matter of moments, these elements transition from an invisible state to that of tiny solid particles, which gently fall towards the bottom. The result? Colored strata, trapped in the sediments, true chemical fingerprints of a world oscillating between suffocating anoxic zones and ephemeral pockets of oxygen. This extreme redox polarization, as scientists call it, outlines a contrasted ocean, both lethally stagnant and chemically alive. But the most fascinating thing is what happens in the depths, away from the light. There, despite the apparent silence, intense chemistry takes place. Without oxygen, dissolved iron and manganese do not oxidize as in a classic ocean. They react differently, with carbonate ions, for example, to form minerals like siderite, an iron carbonate, or rhodochrosite, rich in manganese. These crystals form slowly, sculpted by the laws of weightless geochemistry. But that's not all. Invisible bacteria to the naked eye, called sulfate-reducing bacteria, transform sulfur compounds into sulfides. Consequence: iron combines with sulfur to give birth to pyrite, those golden crystals sometimes nicknamed fool's gold. Their shine is the testimony of a living underground world shaped by infinitesimal oxygen pulses and the discrete breath of microorganisms. Under the ice, the ocean is not dead. It breathes in its own way. A surprising phenomenon of this frozen world concerns colloidal silica, resulting from the transformation of volcanic glass. These are tiny particles of silicon dioxide suspended in the water, which eventually form deposits similar to a gel. During intense submarine volcanic activities, large quantities of this glass are produced. This material, without a crystalline structure, dissolves slowly when in contact with seawater, heat, and time. Under the ice, where the pressure is high and oxygen is rare, this dissolution accelerates, releasing silicate ions that then assemble into silica colloids. The alteration of volcanic glass plays a key role in the chemistry of deep waters. Colloidal silica can capture certain dissolved metals, thus influencing the overall composition of the ocean. When warming or tectonic movement brings these silica-rich waters to the surface, they react upon contact with cooler layers or ion-laden layers, causing the formation of complex mineral structures in the sediments. These particular deposits today allow geologists to trace back to ancient episodes of dissolution, followed by the characteristic reprecipitations of silica. These chemical dynamics also affect the life that persists under the ice sheet. In these oxygen-poor waters, complex animals cannot survive. However, certain extremophile microbes, adapted to hostile environments, exploit the chemical gradients to live. Bacteria use iron or sulfur as a source of energy, forming microbial mats on the seabed or the walls of fissures. These biofilms sometimes facilitate the formation of minerals and locally modify the chemistry. Gradually, a subtle cycle is set in motion, where chemistry, geology, and biology interact continually. Beneath the ice, during these ice ages, the ocean becomes an immense closed laboratory. Iron and manganese, in divalent form, accumulate in oxygen-poor zones, ready to precipitate at the slightest chemical change. Colloidal silica, derived from volcanic glass, slowly saturates the deep waters before fixing in the sediments. Millions of years later, these reactions leave traces, layers of carbonates, sulfides, or silica, inscribed in the geological records. Each mineral deposit tells of a redox fluctuation. Each lens of silica reveals the extent of hydrothermal alteration, and each metallic inclusion illuminates the ancient history of our planet. Imagine a world frozen by extreme cold, where the oceans are almost entirely covered by ice, leaving only a few rare pockets of open water. This icy setting, far from the one we know, is ideal for understanding how life survived. In this polar climate, the biosphere takes refuge in illuminated areas or near underground sources of chemical energy. In this icy world, a few cracks in the ice, called polar leads, become vital openings for life. These cracks are zones of open water surrounded by ice. Normally, light does not penetrate the kilometers, miles of ice. But here, it reaches the ocean. This is enough to sustain microorganisms such as microscopic algae and cyanobacteria. Through photosynthesis, they produce oxygen, essential for other forms of life and underwater biological processes. Even limited, photosynthesis remains vital. It is one of the few sources of organic matter to feed the food chain. In this icy environment, light is scarce and quickly attenuates beneath the ice, forcing life to find other strategies for survival. Only a few microorganisms capable of enduring extreme cold and darkness manage to maintain themselves in these isolated pockets, where temperatures sometimes plunge far below zero. Beyond the illuminated zones, other microbes survive without light through chemolithotrophy. This is a process where energy comes from chemical reactions between minerals. For instance, some bacteria oxidize dihydrogen, a molecule composed of two hydrogen atoms, to produce organic matter. Others use methane or bivalent iron, a form of iron having lost two electrons. These mechanisms allow them to live in total darkness, where light never penetrates. In the great depths, chemolithotrophic activity is particularly intense around hydrothermal vents, located near oceanic ridges where tectonic plates separate. Powerful jets of hot fluids loaded with minerals such as dihydrogen, methane, or bivalent iron meet the icy water and form dense plumes. Microorganisms proliferate there, exploiting these chemical compounds to produce organic matter without ever depending on light. Thanks to chemolithotrophy, life endures even in the absence of light. But oxygen, produced by photosynthetic organisms, remains vital for many more complex species. This is why the rare zones where light still penetrates are crucial. They ensure minimal oxygen production. In this fragile balance, each microbial group depends on the others to maintain a semblance of biodiversity. In these communities, selection favors cyanobacteria, equipped with special pigments, phycobiloproteins. Thanks to them, these microbes can capture light even in very low quantities, a decisive advantage in the almost constant darkness. These pigments work like antennas, absorbing light energy and channeling it to the heart of the photosynthetic process. Thus, these cyanobacteria produce enough organic matter to survive, and sometimes even support other forms of life around them. But these cyanobacteria don't just adapt to the light. In the icy cracks, they must also face extreme cold and a lack of nutrients. To survive, they strengthen their cellular structure, limit water loss, and protect their enzymes from freezing. Some produce antifreeze substances that prevent crystal formation inside the cells. Others modify their membrane to retain fluidity, essential for basic chemical reactions. In these extreme conditions, cooperation becomes essential. Microbes often share their waste or byproducts, which serve as resources for other specialized species. This interdependence optimizes the use of scarce available nutrients and enhances collective survival. Each group becomes a vital link in a fragile network, where unity is strength in the face of an inhospitable environment. During the Great Neoproterozoic glaciation, the planet appears frozen under vast expanses of ice, suggesting that all geological activity is impossible. Yet, forces from deep within manage to break this frozen cap. This is how subaerial volcanoes emerge, with their summits piercing the ice sheet to form surprising flat reliefs called tuyas. A tuya forms when a mantle plume, an upwelling of extremely hot rock, pierces the Earth's crust, despite the ever-present ice. Magma gushes beneath the ice sheet, melts through the water, and carves lava tunnels until it reaches the open air. It is then that the volcano takes its characteristic shape, a flat, almost tabletop summit, born from the eruption through the ice. These structures are born from the brutal confrontation between the heat of magma and the polar environment. Under a thick ice sheet, sometimes a kilometer or 3,281 feet, the pressure initially prevents the magma from rising. But over the course of eruptions, it eventually breaks the ice and forms a cone that emerges to the surface. This clash between fire and ice triggers spectacular reactions, steam, intense heat, and violent geothermal phenomena. In this icy world, the atmosphere is almost devoid of humidity. Water is trapped in the ice caps, and clouds remain rare. The troposphere thus becomes extremely dry. When a volcano is able to release its gases into this desert-like air, the impact can be enormous. Carbon dioxide, a powerful greenhouse gas, warms the atmosphere, while sulfur dioxide forms aerosols, capable of reflecting sunlight and cooling the planet. At the beginning of the glaciation, sulfur dioxide released by volcanoes causes a slight cooling by reflecting some of the sunlight. But this effect is temporary. The aerosols eventually settle. Carbon dioxide, on the other hand, accumulates sustainably. Under normal conditions, it would be partially absorbed by rocks through erosion and rainfall. However, under the ice, these processes are almost at a standstill. Thus, CO2 remains trapped in the atmosphere, gradually strengthening the greenhouse effect. The accumulation of carbon dioxide profoundly changes the climate, intensifying the greenhouse effect even in an already frozen world. Gradually, volcanic heat injects enough gas to disrupt the planet's thermal balance. The few microbes living in geothermal zones feel the effects. Deprived of surface water, they survive thanks to local melting caused by the heat. Around emission zones, a small microbial fauna exploits the hot, nutrient-rich minerals. As mantle plumes multiply, new volcanoes emerge in the ice. Some form actual islands, others remain buried under the ice sheet, but all release carbon dioxide, which gradually accumulates in the atmosphere. Without erosion to absorb it, this continuous emission acts like a climatic time bomb. In the long term, it could suffice to warm the planet and break the grip of extreme cold. Over time, subaerial volcanism causes a slow warming. The accumulation of carbon dioxide eventually fractures the icy barrier, initiating global thawing. During great glaciations, the accumulation of ice exerts enormous pressure on the Earth's crust, which slowly sinks under its weight. This phenomenon, called isostatic deformation, reflects the lithosphere's ability to adjust according to the masses it bears. The thicker the ice cap, the more the crust subsides, sometimes trapping vast pockets of liquid water under the ice in the planet's invisible depths. The pressure of the ice is also manifested by its movement. Under its own weight, the ice cap slowly deforms and spreads towards the edges. The thicker the center becomes, the more the peripheral areas stretch. This sliding is amplified by temperature. Subglacial water acts as a lubricant, facilitating the deformation of the deep layers. Thus, the ice starts to move, silently, but with considerable force. When the ice caps reach a critical size, their weight enhances isostatic deformation, pushing the lithosphere towards the mantle. This slow but powerful process gradually shapes vast subglacial basins. Over time, water trapped in these hollows accumulates and forms lakes buried beneath the ice. The pressure is so strong that it keeps the water in a liquid state, despite temperatures well below zero. When glaciation extends, the lithosphere remains depressed under the weight of the ice cap. But after millennia, a slow process begins, the glacio-isostatic rebound. As soon as the ice stops accumulating or starts to melt, the Earth's crust gradually rises to regain its balance. This adjustment is not instantaneous. It occurs with a delay, sometimes long, between the complete melting of the ice and the rising of the ground. This delay in isostatic rebound can cause major changes. Even if the ice cap starts to melt, the crust remains sunken for several centuries under still significant pressure. During this phase, fractures can form in the rock, especially beneath glacial lakes. Called sublacustrine faults, they result from stresses accumulated during the retreat of the ice. These fissures then open pathways for the circulation of water and sediments. Sometimes, these faults create unexpected drainage routes, particularly near glacier-covered lakes. These lakes form when water trapped under the ice cap, blocked by the thickness of ice and extreme cold, remains trapped under pressure. As long as it does not find an outlet, it stays liquid. But if a fault suddenly opens, the lake can abruptly empty, releasing a devastating torrent of water, broken ice, and suspended sediments. This phenomenon, known as catastrophic drainage, gives rise to glacial slurries, semi-fluid flows of water, crushed ice, and rocks. These icy torrents can travel for kilometers or miles, carrying massive blocks and fine mud and reshaping landscapes in a matter of days. Their erosive force carves deep valleys under the ice, fractures the ice cap, and alters water circulation in the lower layers of the glacier. Beyond the immediate upheavals, subglacial drainage can exacerbate the instability of ice caps. By redistributing the mass of ice, they cause new isostatic adjustments, sometimes opening other faults and pathways for water. If the ice cap is already weakened by warming, the risk of fracturing increases. Water then infiltrates more deeply, lubricating the base of the glacier and locally accelerating its movement, in a cycle that further reinforces glacial dynamics. All these phenomena reveal the fragility of a world dominated by ice. Under pressure, ice caps can suddenly fracture. Buried lakes then become ticking time bombs, releasing in a few hours torrents of mud, water, and ice. These ruptures reshape landscapes and further destabilize the ice mass. Internal pressure and instability remain key forces in the evolution of ice caps during the Neoproterozoic. In this landscape, frozen by immense ice caps, an irreversible change is brewing. We are at the end of the Sturtian glaciation, one of the coldest periods in Earth's history. The atmosphere, frigid for millions of years, approaches a critical threshold. Carbon dioxide has accumulated so much that it triggers a powerful warming. When its pressure exceeds 0.12 bar, the trapped heat becomes sufficient to start melting the ice. This tipping point, called the radiative threshold, corresponds to energy received at about 350 watts per square meter, or 1,542 BTUs per square foot. This threshold marks a rupture in the balance between solar energy received and the light reflected by the frozen surface. At the time, the planet is almost entirely covered with ice, giving it a very high albedo. But gradually, dark dust transported by the wind or from volcanoes accumulates on the ice. As it sublimates, it reveals the pure ice below, locally modifying the reflection capacity and accelerating heat absorption. This seemingly minor phenomenon triggers a virtuous cycle of warming. When the ice darkens, it reflects less light and absorbs more heat, which accelerates its melting. Near the equator, the air sometimes exceeds 0 degrees Celsius, 32 degrees Celsius, creating thin pockets of water on the surface. The ice layer thins, and the temperature difference between poles and tropics decreases. Gradually, a planetary upheaval begins, a turmoil that will transform the entire biosphere. Long before the emergence of complex life, Earth already harbors microbes capable of surviving extreme conditions. Melting creates areas of open water where primitive bacteria and algae proliferate. Despite the low light, they perform photosynthesis and enrich the water with oxygen, a key element for future evolution. As the ice retreats, these ecosystems expand, colonizing new spaces and silently preparing the ground for major advances in life. Meanwhile, the distribution of heat changes. Equatorial seas, once frozen, begin to thaw, reducing solar reflection. On a geological scale, this shift is rapid. Within a few millennia, the tropical zone widens, transferring more heat towards the poles. The temperature difference narrows, weakening the icy winds that maintain the cold. As the atmosphere becomes enriched with carbon dioxide, the climate softens, opening new niches for life. As the tropics are freed from ice, a striking contrast emerges between the still frozen areas and those where water flows again. This transition disrupts the young biosphere. In the cleared regions, a great variety of microorganisms proliferate. Direct light stimulates photosynthesis, and productivity explodes. New food webs form, diversity multiplies. Algae and microbes take advantage of the free water to quickly expand and colonize this world in transition. Concurrently, the reduction of the thermal gap between the equator and the poles accelerates warming. Polar regions, once locked in a frozen night, experience slight seasonal variations. Gradually, cracks form in the sea ice, and a milder climate sets in. On the glaciated continents, meltwater sculpts new landscapes, carving channels into the glacier surfaces. The end of the Sturtian glaciation marks more than just a simple warming. It is a profound climatic shift. Carbon dioxide reaches a critical threshold, tropical ice begins to melt, and dark dust accelerates solar absorption. The thermal contrast fades. Earth, slowly but surely, emerges from one of the coldest episodes in its history. The planetary thaw begins when the ice sheet melts due to sustained warming. The temperature rises above 0 degrees Celsius, 32 degrees. The ice breaks and water vapor increases in the atmosphere. This surplus vapor traps more heat, further accelerating the melt. As the ice recedes, the dark surface absorbs solar energy. A vicious cycle sets in, propelling Earth towards a world almost entirely freed from ice. Water vapor is one of the most powerful gases for trapping heat. Present in the lower layers of the atmosphere, it enhances warming by holding the energy reflected by the surface. This surplus heat accelerates ice melting, exposing more soil and open water. These dark surfaces absorb far more radiation than snow. The result? Warming intensifies in a self-perpetuating cycle. As the ice melts, the oceans warm and expand. Warm water occupies more space than cold water. Even without the total melting of the ice caps, sea levels rise significantly. It is estimated to rise by more than 100 meters, 328 feet. Lands once frozen are submerged, coastal plains disappear, and ancient polar regions transform into bays or inland seas. Glacial melt releases vast volumes of fresh water, swelling rivers and turning them into powerful torrents. These floodwaters erode the soils laid bare by the retreat of ice, carving deep and wide valleys. Unlike the V-shaped valleys of classic rivers, these U-shaped forms, called paleovalleys, bear the dual imprint of water and glaciers. They remain today as spectacular traces of this geological transition. In these valleys, water flows with force. It carries freshly detached sediments from the slopes, depositing them downstream in the form of deltas. These fertile areas become refuges for primitive algae and small filter-feeding organisms. The warmed, nutrient-rich water stimulates life. The most adaptable species thrive, while those tied to the cold retreat to more stable habitats, far from the rapid upheavals. The accumulated water vapor in the atmosphere triggers torrential rains, feeding the rivers and swelling the waterfalls. The soaked soils, weakened by melting, give way under pressure. Landslides disrupt the slopes and carry away significant masses of organic material. As it decomposes, this material releases precious nutrients for the riverbank life. Thawing thus initiates a rapid, cascading transformation of landscapes and habitats. On the flooded coasts, vast swamps emerge, conducive to new life. Plants similar to algae proliferate in the shallow, light-bathed waters. Small invertebrates colonize the nutrient-rich sediments. The heat, amplified by water vapor, allows numerous species to expand. Meanwhile, the ice pack fractures, albedo falls, and melting accelerates even more. The more the ice recedes, the more humid the atmosphere becomes, warm air rises, making the weather unstable. In some regions, monsoons settle and unleash almost continuous rains, turning the plains into swamps. Elsewhere, abrupt alternations between droughts and floods appear. This instability, fueled by the greenhouse effect, accelerates ecological upheavals and profoundly reshapes the planet's landscape. Eventually, the expansion of oceans, ice melting, and increasing humidity transform the planet. The ice caps retreat towards the poles, leaving continents reshaped by rivers and floods. The ancient ice packs become inland seas. The glacial valleys testify to a vanished past. This great thawing opens a new chapter, a milder world where fauna, flora, and geography reinvent themselves. At the end of the Sturtian glaciation, the melting of the ice and the rapid rise of the oceans left behind very peculiar deposits, cap carbonates. Their chemical composition and structure amaze with their uniqueness. Upon discovery, researchers immediately recognized clear markers of the post-glacial world, revealing the environmental upheavals and processes that shaped them. When the ice caps started to melt, large quantities of relatively warm water flooded the oceans. These waters, rich in minerals from rock erosion, brought calcium and bicarbonates in abundance. The ocean then became oversaturated, too much matter to stay in solution. Like an overloaded broth, seawater spontaneously began forming carbonate crystals, precipitating the first cap carbonates. In this context, dolomite and calcite were deposited over vast areas, forming the so-called cap carbonates, because they cap directly on glacial sediments. Fine, wavy layers are often observed, stacked like the pages of a book. These micro-undulations reflect the rapid variations in marine chemistry. Each stratum reflects a specific moment of sedimentation, witnessing a rapidly transforming post-glacial environment. Besides the laminations, calcite crystal fans are also observed, genuine crystalline fans rising perpendicularly to the sedimentary layers. They arise from rapid precipitation in saturated water, giving the crystals a tapered shape that radiates in clusters. Imagine an ancient ocean floor covered with these sparkling mineral bouquets, like natural sculptures shaped by extraordinary chemistry. By studying these rocks, geologists detected a marked isotopic anomaly. It is the signature of carbon-13 which drops sharply. The measured values, between 5 and 7 per mil, indicate that heavy carbon is far less present than expected. This imbalance suggests a major disruption of the biosphere and oceans at the very moment of glacial melting, as if life had suddenly ceased to function normally. This phenomenon, known as the SEEDEX excursion, reflects a strong depletion in carbon-13 immediately following the retreat of the ice. Several elements explain this. The melting injected large amounts of fresh water, disrupting the chemical equilibrium of the oceans. The decomposition of released organic matter enriched the waters with carbon-12. Finally, massive microbial blooms favored isotopic fractionation, further accentuating this drop in the values measured in carbonates. These mechanisms amplified the isotopic anomaly observed in the post-Sturtian cap carbonates. They reveal an ocean profoundly transformed. The rapid rise of the seas submerged the continents, disrupting coastal environments. The dissolution of rocks and the influx of nutrients favored the massive precipitation of dolomite and calcite. These rocks are distinguished by fine, wavy laminations and superb fan-shaped crystals. The low values of carbon-13 measured confirm an unprecedented biogeochemical disturbance, evidencing radically different marine conditions from those we know today. These deposits mark a major turning point after the Sturtian glaciation, heralding the emergence of a new biological dynamic on Earth. Between approximately 717 and 650 million years ago, the Earth experienced a glacial calm following the Sturtian freeze, which had locked vast lands and oceans. This interglacial period, known as the Sturtian-Marinoan, marks the progressive resumption of oceanic and atmospheric circulations, previously slowed by the extreme cold. The retreat of the ice sheets freed wide marine corridors, reviving the exchanges of water and the distribution of essential nutrients for marine life, such as phosphorus and iron. During this period, the melting of the ice released significant sediments and mineral particles, enriching seawater with key nutrients. Phosphorus, essential for cellular energy, and iron, indispensable for the respiration of many organisms, were massively diffused. This nutrient boost increased the biological productivity of the oceans, supporting the growth of planktonic microorganisms. New food chains formed, and this effervescence favored the progressive evolution of marine life. The rise of microorganisms, particularly cyanobacteria and other planktonic forms, led to a notable increase in oxygen production. This surplus of oxygen favored the emergence of more complex metabolisms, paving the way for forms of life more demanding in energy. Although oxygen levels remained lower than today, this increase marked a major turning point. Aquatic ecosystems gained in diversity, and the chemistry of the oceans became progressively more favorable to the blooming of emerging species. To better grasp this dynamic, one must recall the crucial role of ocean circulation in the distribution of heat and nutrients. When the ice retreats, the marine basins open to new currents that bring warm water from the tropics to the high latitudes. This mixing, both vertical and horizontal, favors the upwelling of nutrients from the depths, a phenomenon known as upwelling. This process stimulates the growth of plankton, an essential driver of the marine food network. In parallel to this oceanic mixing, the planet entered a phase of climatic rebalancing marked by milder temperatures, often described as subtropical. The air and water slowly warmed, creating more favorable conditions for biodiversity. Glacial remnants persisted, but organisms adapted to temperate environments gained ground. On the still fragmented continents, new river networks appeared, transporting nutrients to the neighboring seas. Gradually, a mosaic of ecological niches emerged, promoting the diversification of life. As the currents intensified and the melting ice revealed new coasts, deep biogeochemical upheavals emerged. The marine ecosystems, stimulated by the massive arrival of nutrients, developed rapidly, altering the chemistry of the oceans. Photosynthetic activity intensified, absorbing more dissolved carbon dioxide and releasing more oxygen. This surplus led to a slight increase in atmospheric oxygen, a crucial turning point for the emergence of multicellular life. Although levels remained low compared to today, this transition paved the way for richer biodiversity. In this context, the increase in biological productivity also leads to an increased sedimentation of organic matter at the bottom of the oceans. As these debris accumulate, the recycling of nutrients intensifies, triggering a virtuous circle. The more life develops, the more it modifies marine chemistry to its advantage, reinforcing its own expansion. This phase of enrichment coincides with several evolutionary innovations, such as the emergence of microorganisms better adapted to fluctuations in salinity, or the diversification of microbial communities colonizing the vast, newly exposed coastal areas. Ultimately, The Sturtian-Marinoan interglacial appears as a phase of relative stability, contrasting with the extreme upheavals that preceded it and those to come. The now milder temperatures oscillate around subtropical values, conducive to burgeoning biodiversity. Although modest, the increase in oxygen plays a key role in the emergence of more complex ecosystems. This lull offers a salutary respite to life forms before the next climate crises. For despite this apparent stability, the climate remains fragile, and the Earth is already preparing to flip toward new, profound upheavals. During the interglacial interval between the Sturtian and Marinoan glaciations, between 717 million and 650 million years ago, the Earth experienced a period of relative warming conducive to the emergence of new forms of life. In this milder climate, despite an atmosphere still poor in oxygen, several major biological evolutions disrupted the nascent ecosystems. The appearance of multicellular green algae, the expansion of stromatolitic microbial mats, and the diversification of redox-dependent genomic systems marked a turning point in the history of life. During this period, multicellular green algae, often referred to as prasinophytes in their primitive form, began to develop in shallow seas. Unlike their unicellular ancestors, these organisms exhibited several specialized cells, cooperating to capture sunlight and produce energy. This process, called photosynthesis, allows for the conversion of carbon dioxide dissolved in water into sugars. By releasing oxygen in return, these algae contributed to enriching the environment and initiating new ecological dynamics. The presence of these algae in the sediments of that time testifies to a gradual adaptation to constantly evolving marine environments. Geological records reveal the proliferation of microscopic plant structures forming true multicellular colonies. This more complex cellular organization offered them a better ability to capture nutrients and light. Moreover, their ability to release oxygen helped modify ocean chemistry, making it more conducive to the establishment of other life forms. Thus, these green algae actively participated in the transformation of emerging ecosystems. In parallel, stromatolite mats experienced a strong expansion on carbonate platforms. These formations developed through the accumulation of microorganisms, mainly bacteria capable of precipitating minerals. Over time, these colonies create layered calcareous structures, taking the form of domes, columns, or thin layers. During the interglacial interval, the milder temperature and accessible shallow areas provided these communities with an ideal environment to thrive and shape the first primitive reefs. These structures served as a refuge for many microorganisms while playing a key role in nutrient recycling. The bacteria they harbored were capable of fixing and releasing essential compounds, maintaining a favorable ecological balance. By covering vast areas, stromatolites also contributed to enriching the water with oxygen and modifying its chemical composition. This network of interactions would have extensively prepared the biosphere for the emergence of more complex organisms, marking a decisive step toward future evolution. In parallel with the evolution of microbial and algal communities, the diversification of metabolic mechanisms related to redox reactions marked a crucial step. These reactions allow organisms to draw or store energy from chemical compounds, such as oxygen or other oxidizing agents. At this point in Earth's history, this biochemical innovation provided new metabolic tools that greatly favored evolution. Concretely, these new metabolic pathways allowed the utilization of a wider variety of molecules well beyond photosynthesis. Innovative enzymes and transport proteins facilitated the capture of electrons from various chemical compounds. Some bacteria, for example, could oxidize minerals or reduce sulfur compounds to produce energy. This metabolic diversity offered a crucial advantage in unstable environments where oxygen, nutrients, and energy sources varied significantly. Symbiotic interactions also played a key role in this diversification. Some algae or bacteria lived in association with other organisms, sharing their resources and enhancing their protection. These alliances accelerated the transformation of ecosystems, creating a collective evolutionary dynamic. By uniting their metabolic forces, some species were able to settle in more hostile environments. The interglacial period thus saw the birth of unprecedented biological partnerships, announcing increasingly complex symbiotic exchanges. Let's go back nearly 650 million years to the dawn of the Marinoan glaciation, one of the most extreme the planet has ever experienced. Before the ice extended to the equator, a series of geological and climatic upheavals laid the foundations for this ice age. To understand its origins, one must first observe a world still marked by the fragmentation of the supercontinent Rodinia, a remnant of the Neo-Proterozoic era. At this stage, Rodinia was slowly breaking apart, giving rise to several distinct continental blocks. This separation caused a major reconfiguration of coasts and ocean basins. Rifts appeared, opening up new marine spaces. This transformation altered ocean currents, which redistributed heat across the planet. But as the continents became independent, their position and geological nature influenced exchanges between the atmosphere, the liquid waters of the hydrosphere, and the solid crust of the lithosphere. It is upon contact with air and rain that continental rocks undergo weathering, a set of chemical and physical reactions that decompose their minerals. At that time, this phenomenon intensified due to acid rains provoked by volcanic activity. The volcanoes, activated by moving tectonics, released gases like sulfur dioxide, which combined with rainwater to form corrosive precipitation. By attacking rocks on the surface, they released essential ions carried by rivers to the oceans. This enriched marine fertility while changing the chemistry of the water. In this context, one essential process stands out: the capture of carbon dioxide by silicate rocks. When minerals like feldspar react with CO2 dissolved in water, they transform into clays and trap this gas in the form of carbonates. This mechanism, known as the silicate thermostat, acts as a natural long-term climate regulator. The higher the reliefs and the more they are subject to erosion, the more intense the CO2 consumption becomes. At that time, recent volcanic terrains and tectonic activity greatly reinforced this process, absorbing more gas from the atmosphere. Understanding the impact of carbon dioxide is crucial to explain the entry into a new glacial phase. This gas traps heat emitted by the Earth, helping to maintain a stable climate. When it becomes too scarce, the greenhouse effect weakens and the planet cools. Around 650 million years ago, geochemical data indicate that its concentration dropped below 0.01 bar, a minimal but decisive value. This partial pressure reflects its share in the total atmospheric gases. At this stage, any tiny variation sufficed to disrupt the global thermal balance. To better understand this drop in carbon dioxide, imagine an Earth without terrestrial vegetation. The continents only host small microbial colonies, living on moist surfaces or in extreme environments. In the oceans, a few primitive algae and planktonic organisms begin to appear, but complex life remains absent. Although they practice photosynthesis, these aquatic beings are not sufficient to regulate CO2 on a planetary scale. Without forests or massive biomass, this role largely falls to geological mechanisms, such as rock weathering, to maintain the balance between the atmosphere, oceans, and sediments. The combination of continental dislocation, active volcanism, and intense weathering pushes the climate toward major cooling. The drop in carbon dioxide, amplified by the expansion of snow-covered surfaces, increases the reflection of solar energy. The glaciation accelerates. The Earth system, unbalanced, is about to tip. According to geological data, the Marinoan glaciation set in with exceptional rapidity, exceeding that of the older Sturtian glaciation. About 650 million years ago, a sudden cooling led to the formation of an immense ice cap covering continents and oceans. Unlike the slow progression of ice during the Sturtian period, the Marinoan saw nearly the entire planet frozen in less than 500,000 years, an instant on the geological timescale. To grasp the abruptness of this glaciation, one must imagine Earth almost suddenly tipping into a polar climate. If the Sturtian glaciation set in more slowly, the Marinoan seems to have been triggered by slight changes, a minute drop in CO2 or a modification in ocean currents. These variations would have been enough to cross a critical threshold. The climate system then runs away. The albedo increases. Less energy is absorbed, the atmosphere cools further, and the ice continues to spread. A glacial, vicious circle sets in, reinforcing the grip of cold. From a geological standpoint, this abrupt transition profoundly transforms Earth's surface. The early phases of the Marinoan see the sea ice covering the oceans, then merging with continental glaciers to form an immense reflective shield. Unlike the slow progression of Sturtian glaciation, the Marinoan glaciation is rapid. In a short amount of time, nearly all ice-free marine surfaces disappear. It is estimated that at the equator, the ice thickness reached between 1.5 kilometers, 1 mile, and 2.5 kilometers, 2 miles. Although these figures remain approximate, they testify to a much larger ice cover than seen today, even in the most extreme polar regions. Under several kilometers, miles of ice, glacial activity carves immense structures called giant ice-buried channels, or glaciotectonic megastructures. They originate from pressurized meltwater flow, carving long, sinuous corridors guided by the seabed's relief. In these galleries, geothermal heat and hydrothermal flows sometimes maintain pockets of liquid water. These zones could host extremophile microbes capable of surviving without light in the cold through chemical reaction energy. This phenomenon is reminiscent of deep ecosystems seen today beneath Antarctica. What most distinguishes Marinoan glaciation from Sturtian is the speed at which the Earth found itself almost entirely frozen. Researchers suggest that the position of the continents at that time, due to plate tectonics, favored sudden cooling. Their arrangement would have amplified heat loss. Simultaneously, the greenhouse gas concentration, notably carbon dioxide, was too low to slow this temperature drop. The usual climate buffering effect was not enough to prevent the transition to global glaciation. The impact of this glaciation on life remains difficult to determine. Organisms dependent on light, such as algae, faced significant pressure, with the ocean being almost entirely covered in ice. Some microorganisms may have survived in pockets of open water, near fractures in the ice sheet, or in dimly lit subglacial channels. Life likely retreated into restricted niches, hindering the diversification of the biosphere. Only a few simple animals, like sponges or small multicellular organisms, might have subsisted thanks to oxygen bubbles trapped in the water. Without terrestrial vegetation, the continents resembled icy deserts, completely barren. At its peak, the Marinoan glaciation covered nearly the entire ocean, with an ice sheet several kilometers or miles thick. The oldest marine sediments testify to a collapse in ocean circulation. In other words, no more mixing between surface waters in the depths, no more exchange with the atmosphere. The ocean, isolated beneath the ice, became depleted of nutrients, threatening the survival of marine ecosystems. During the Sturtian, the glaciation was widespread but less homogeneous. The Marinoan, however, marks an extreme shift, considered one of the most severe Snowball Earth episodes in the planet's history. During this period, the oceans were entirely covered by a thick layer of ice. This covering almost completely blocked the sun's rays, preventing the water from warming. In depth, temperatures often dropped below 2 or 3 degrees Celsius, or 36 degrees, or 37 degrees. Yet, ocean circulation remained surprisingly stable. A slow and steady current, known as laminar circulation, took shape, guided by subtle variations in large-scale salinity. This laminar circulation mainly results from differences in salinity. Water mixing with warm underwater sources became enriched with dissolved minerals, while ice formation rejected some of the salt. This created areas of varying salinity. Denser, saltier layers of water slowly slid beneath others, forming large sheets without vertical mixing. This discrete, almost invisible flow nonetheless played a key role in the transport of heat and nutrients. On a global scale, the planet remained frozen in enduring cooling, which stabilized the water masses. Normally, currents rely on temperature differences between the equator and the poles, but under the ice, these differences faded. Circulation became mostly horizontal. Saltier, denser waters plunged, while less salty ones remained on the surface. A slow thermohaline circulation settled, dictated by salinity, gravity, and a climate frozen by cold. Despite the ice, underwater volcanoes continued to emit gases from magma, such as carbon dioxide and methane, which dissolved in the water. Unable to escape, they accumulated in deep pockets, sometimes in extreme concentrations. Over time, a simple change in pressure or temperature could trigger their sudden release. Bubbles then briefly rose in the water, before being trapped under the ice sheet. Methane, a simple gas composed of carbon and hydrogen, played a key role in this ice-covered ocean. Normally, it evaporated into the atmosphere, but here it remained trapped in depth. Some specialized bacteria used it as an energy source, transforming it into organic matter. This process, called chemosynthesis, is common near black smokers, hydrothermal vents rich in sulfur compounds. These microbial communities fed other forms of life adapted to the darkness, creating genuine biological oases beneath the ice sheet. Under the ice, another phenomenon transformed the ocean floors. It's the formation of metallic deposits around hydrothermal sources. Fluids from magma transported iron, copper, zinc, and sulfur in large quantities. Upon meeting the colder seawater, these elements quickly precipitated, forming sulfides that accumulated in crusts or layers. Over time, these deposits formed actual reliefs, sometimes comparable to bright hills under the light. These zones played an essential role in the circulation of metals and offered life niches in this icy universe. These metallic deposits are accompanied by ecosystems adapted to the intense heat of the underground. Near hydrothermal vents, the water sometimes reaches several hundreds of degrees, yet remains liquid due to pressure. In these overheated pockets, hyperthermophilic microbes exploit the chemical energy from minerals and gases emanating from the depths. Invisible but essential, they maintain the local chemical balance and form the base of a microscopic food chain. Further down, where the heat decreases, mesophilic bacteria interact with dissolved iron and sulfur, revealing an underground life without light, but very active. During the Marinoan glaciation, while Earth was almost entirely frozen under ice, an essential question arises. How could life survive in such extreme conditions? For many, it is difficult to imagine that at the heart of a frozen desert, microscopic organisms continued to thrive. Yet, these rudimentary forms demonstrated an incredible capacity for adaptation. Three key elements explain this persistence: pockets of liquid water near mid-ocean ridges, chemosynthesis developed by certain archaea using dihydrogen and sulfur, and the possible existence of brine channels. These unexpected refuges are found near mid-ocean ridges, long volcanic chains located in the heart of the oceans. Where tectonic plates diverge, magma rises and heats the water, even under a thick ice layer of 1.5 kilometers, or about 1 mile. In some points, the temperature remains above zero, forming true underwater oases in this icy world. Charged with minerals, this warmer water allows specialized bacteria to survive by relying on chemical reactions typical of these extreme depths. In these light-deprived depths, some archaea have evolved to exploit the energy of chemical reactions between seawater and volcanic fluids. These microorganisms, among the oldest on Earth, use chemosynthesis, a process that transforms compounds like dihydrogen or sulfur into energy without light. It is the underground equivalent of photosynthesis. Under the ice, this mechanism becomes one of the few sources capable of sustaining life. Chemosynthesis occurs near the ridges, where this gas, released by hydrothermal vents, is abundant. Archaea, thanks to specialized enzymes, decompose it and extract energy from it. They also exploit dihydrogen, resulting from the contact between mineralized water and subsurface heat. This mixture circulates within volcanic fissures, forming hot jets rich in dissolved elements. These microbes support a local food network by producing organic matter or recycling residues useful for other species. But life is not limited to volcanic zones. Even under the thick ice, it is thought that thin pockets of salty water persist, maintained in a liquid state by pressure and high salinity. As ice forms, it expels the salt, but brine channels saturated with brine remain. Their high salt concentration prevents the water from freezing, even at temperatures close to 10 or 15 degrees C, 14 or 5 degrees F. These tiny corridors could serve as refuges for microbes thanks to a natural antifreeze effect linked to salinity. In these dark, oxygen-poor channels, survival depends on extreme strategies. The main candidates are psychrophilic bacteria or archaea, capable of thriving at very low temperatures. Their membrane contains flexible fatty acids that prevent stiffening, and their enzymes remain active even below 0 degrees C, 32 degrees F. To resist ice, they produce antifreeze proteins and concentrate solutes that protect cellular water and vital structures. Although no direct fossil evidence confirms the existence of brine channels during the Marinoan, studies conducted in current polar regions make this scenario plausible. Today, in the Arctic and Antarctic ice, we observe dust, algae, and bacteria trapped in these channels. Scientists believe a comparable phenomenon might have occurred on a planetary scale, offering a refuge to microbial communities. Thus, despite the extreme cold, a living microcosm may have continued to thrive beneath the ice. Through three mechanisms, the heat of the ridges, chemosynthesis, and brine channels, life managed to survive the Marinoan Great Glaciation. It retreated into dark refuges, enduring one of the Earth's most severe climate crises. These extreme environments, as isolated as they were, offered the most resilient organisms a chance to endure. This tenacity allowed evolution to continue, paving the way for the complex forms of life that would soon transform the planet. At this distant time, the Earth is still frozen beneath ice, plunged into extreme cold. However, volcanoes remain active and slowly release carbon dioxide, a potent greenhouse gas. Gradually, this gas accumulates in the atmosphere until reaching critical levels, initiating the end of the glaciation. Now, we will explore how this rise in CO2 occurred and what role it played for the life forms still present at the time. Volcanic degassing comes from magma rising from the Earth's mantle. Upon reaching the surface, it releases large quantities of carbon dioxide. During this glacial period, it is estimated that the planet released about 0.3 gigatons, 331 million tons, of carbon per year into the atmosphere. However, with the continents covered in ice, rocks could no longer capture this gas through chemical weathering. This natural mechanism, which normally stabilizes the climate, was virtually at a halt. As a result, CO2 accumulated in the air without a real break. Meanwhile, the frigid temperatures dry out the atmosphere. Rain becomes rare, and water trapped in glaciers no longer participates in the erosion of rocks. Yet, this process is essential for extracting carbon dioxide from the air. The volcanoes continue to emit it at a steady rate, but natural regulatory mechanisms are at a standstill. Thus, CO2 accumulates over millennia, causing a gradual rise in its concentration in the atmosphere. According to models supported by geological data, the partial pressure of carbon dioxide would have reached between 0.12 and 0.14 bar, levels far above the few hundred ppm measured today. In the Neoproterozoic, this gas becomes a major climate actor. It acts like a thermal lid, trapping heat and slowly raising temperatures. Even under a thick ice cap, the greenhouse effect eventually reverses the trend. Gradually, the planet prepares to emerge from glaciation. If the ice does not melt immediately, it is due to its powerful mirror effect, the phenomenon called albedo. As long as this albedo remains high, the Earth stays cold, despite the increase in carbon dioxide. It's a tug of war between icy reflection and the greenhouse effect. CO2 eventually wins out, but it requires extreme concentrations to break this resistance and finally trigger deglaciation. At this time, the Earth still harbors no complex animals or plants, but some forms of microbial life resist. They are found in extreme refuges, under the ice, around hydrothermal vents, or in tiny pockets of liquid water, preserved from deadly cold. There, microbes survive using either the diffuse glow of light filtered through the ice or the chemical energy released by volcanic gases and minerals. But outside these oases, everything is frozen. Life is in stasis. This is evidenced by ancient sediments revealing a sharp drop in photosynthesis at a planetary scale. Carbon-13 analyses reveal a troubling phenomenon. The biological pump, this natural mechanism that sends carbon from surface waters to the ocean floor, has practically stopped. Normally, plankton captures carbon dioxide to create organic matter, which eventually settles in sediments. This is how life contributes to climate balance. But under the thick ice sheet, light no longer penetrates. Photosynthesis declines, microorganisms perish, and carbon remains trapped in the water. Geological cores, extracted from various locations around the globe, retain the trace of this major imbalance. These geological cores hold the trace of an almost stalled biosphere. Without plankton to capture carbon dioxide, the ocean no longer plays its role as a reservoir. Meanwhile, volcanoes continue releasing gas into the atmosphere, and as the frozen surface prevents its absorption, carbon dioxide accumulates more and more. For millions of years, it piles up to reach a critical threshold. At that moment, the greenhouse effect becomes so intense that it finally breaks the cold cycle. The Earth then begins to slowly warm. In summary, during this strange period when Earth resembles a snowball, two opposing forces play a decisive role. On one side, volcanoes continue to relentlessly release carbon dioxide. On the other, life, weakened by the cold and deprived of light, no longer manages to capture this gas. Result: CO2 accumulates. Its concentration gradually rises to spectacular levels, between 0.12 and 0.14 bar. In the oceans, carbon-13 isotopic records confirm the collapse of biological activity, and the more the pressure of this gas increases, the more the icy grip begins to crack. The Earth is then slowly preparing to shift toward major warming. At the end of the Marinoan glaciation, Earth experienced a rapid warming of over 50 degrees C or 122 degrees in less than 100,000 years. This shift was caused by the progressive accumulation of volcanic carbon dioxide. This gas, trapped under a thick layer of ice, eventually reached a critical level. Once the ice pack was breached, the decrease in albedo intensified solar absorption, triggering a rapid rise in temperatures. The melting of the ice led to strong evaporation, releasing water vapor, a potent greenhouse gas. This vapor intensified the warming, triggering violent rains. The lands recently freed from ice underwent rapid erosion, carrying away soils and accelerating chemical weathering. The dissolved minerals released calcium and magnesium, which then formed new rocks. This process allowed for capturing part of the carbon dioxide and initiated a gradual regulation of the climate. The sudden warming led to a massive influx of sediments to the sea floors. These materials, transported by violent currents, formed heterogeneous deposits called glacial-marine conglomerates, containing large blocks encased in clay and silt. Underwater landslides and mud avalanches helped seal this period within the rocks. This moment marks the end of an extreme glacial era and the beginning of an intense warming that will deeply alter the chemical and thermal balance of the oceans. The thawing of the ice had a profound impact on the biosphere. Extremophile microorganisms took advantage of nutrients released by erosion to colonize the liberated oceans. This surge in productivity would have favored an increase in oxygen, laying the groundwork for future ecological evolutions. The rupture of the Marinoan glaciation thus marks a turning point, both geological and biological. The rapid melting of the ice also caused an uplift of the continents, perturbing the oceans and triggering tectonic faults. This period was marked by a chaotic climate with violent storms. Thanks to the weathering of rocks, carbon dioxide began to decrease, allowing the planet to gradually emerge from the furnace and reach a new climatic equilibrium. The exit from the Marinoan glaciation highlights the force of climate feedbacks. Water vapor, carbon dioxide, and albedo accelerated the warming. The violent rains eroded the freshly cleared lands, triggering massive chemical weathering. This process gradually reduced the carbon dioxide concentration, initiating a slight cooling. Thus, the climate spiraled before beginning to stabilize. The swift strike of the ice caps disrupted the salinity of the oceans, disturbing microbial ecosystems. Yet, In coastal areas, some species found a new balance. The return of light and the abundance of nutrients allowed opportunistic bacteria and algae to colonize these environments, forming vast microbial mats. This renewal of microscopic life helped enrich the atmosphere with oxygen, laying the foundation for more complex future ecosystems. This episode underscores the capacity of life to rebound, even under the most extreme conditions. After this abrupt deglaciation, the Earth experienced a more temperate phase, although temporary. The glacial-marine conglomerates formed at that time provide valuable evidence of the extreme climatic upheavals that occurred then. For scientists, this episode shows how quickly the planet can shift from one state to another. It also highlights the importance of greenhouse gases and the water cycle in climate regulation. Above all, this explosive transition laid the groundwork for new forms of life, initiating a profound transformation of the biological world. In the Post-Marinoan geological strata, a striking contrast appears. Glacial diamictites abruptly give way to dolomite-rich cap carbonates. These carbonate layers signal an ocean suddenly enriched with calcium and magnesium, 6,894 giga or 12,429 giga, triggering massive precipitation. This geological transition symbolizes the end of glacial domination and the beginning of a new era marked by rapid changes in ocean chemistry. It is also a sign of a biosphere ready to be reborn as Earth embarks on a shift toward a world of renewal. The dolostones, carbonate rocks made of dolomite, dominate in the post-glacial cap carbonates. Formed by the precipitation of calcium and magnesium, the dolomite was rapidly deposited following the melt, stimulated by ions released from continental erosion. The thickness of these rocks reflects a dramatic chemical upheaval in the oceans. This sudden accumulation attests to a major climatic turning point and leaves a lasting imprint in the geological records. It illustrates the power of post-glacial transitions and the role of interactions between the atmosphere, continents, and oceans in Earth's evolution. At the boundary between dolostones and diamictites, strange crystalline formations sometimes appear, acicular sunburst crystals. Thin as needles, they organize into radiant patterns, resembling small mineral suns. Their rapid growth indicates a sudden chemical event, an oversaturation of waters with ions, causing near instantaneous precipitation. In this suddenly ion-charged ocean, minerals solidified swiftly, leaving behind these brilliant structures. True flashes frozen in rock, they tell of the silent violence of a global-scale chemical shift. Behind these visual structures lie valuable geochemical clues. Researchers rely particularly on strontium isotopes, an element released into the ocean by continental erosion. These isotopes, which are variants of the same atom with different numbers of neutrons, leave a trace in the carbonates formed at that time. The ratio between strontium-87 and 86 thus becomes a true fingerprint of these erosion processes. It offers a unique record of ancient geological upheavals, becoming an essential marker of the intensity of past erosion. In Marinoan cap carbonates, the strontium isotopic ratio shows marked variations, called excursions, which indicate rapid alteration of the continents. When the ice retreats, vast rocky surfaces are suddenly exposed to rain, runoff, and temperature fluctuations, releasing significant amounts of strontium into the waters. The carbonates that precipitate then retain the signature of this phenomenon. This discovery has revealed the unprecedented scale of post-glacial erosion, an event so intense that, according to several specialists, it had never been observed throughout the Neoproterozoic. This accelerated erosion has several major effects. It enriches the oceans with nutrients such as phosphorus and iron, stimulating the growth of plankton and bacteria. It also alters marine chemistry, causing the rapid formation of carbonate deposits. Finally, by releasing volcanic carbon dioxide, approximately 4,500 degrees or 8,132 degrees, and halting its capture in the ice, it contributes to global warming. These post-glacial carbonate formations thus reveal a geological and climatic engine at work, illustrating an intense and transformative dynamic of the planet. When the ice retreats, life tries to reclaim its space. The newly liberated coasts welcome photosynthetic microbes forming pigmented mats. With nutrients brought by erosion, these microorganisms proliferate, releasing oxygen and triggering complex chemical reactions. Cap carbonates retain the trace of this resurgence, revealing once again dynamic marine ecosystems. It is the dawn of an ecological renewal, a vital breath spreading over a planet reborn after the grip of cold. Acicular sunburst crystals and marked variations of strontium testify to a profoundly altered ocean chemistry due to massive continental erosion. This alteration has transformed coastal areas, transporting mineral-rich sediments into the ocean. The accumulated dolostones preserve the memory of this dynamic, offering a window into the exchanges between the atmosphere, ocean, and continents. Each layer tells the story of our Earth in transformation. As the Earth frees itself from the immense ice sheets, a chemical upheaval occurs in the oceans and atmosphere. The climate softens, polar mists dissipate, and the composition of elements changes. One of the key markers of this transition is the delta 34 sulfur, which measures the isotopy of sulfur in marine sulfates. This value reflects the balance between biological and geological processes, such as the formation of pyrite, a mineral of iron and sulfur that appears in low oxygen environments. Shortly after the ice's regression, scientists observe a positive peak of delta 34 sulfur, with an enrichment of about 15 per thousand in heavy sulfur. This signal reflects intense pyritization. Microbes consume sulfur compounds and fix light sulfur in pyrite, leaving heavy sulfur in oceanic sulfates. This isotopic imbalance marks a disruption of the exchanges between life and geology, revealing a massive transfer of sulfur to sediments and a deep readjustment of biogeochemical cycles. This intense pyritization is often accompanied by massive burial of organic matter, depleting the water of oxygen but stimulating the formation of pyrite. Once trapped in sediments, this carbon no longer forms carbon dioxide, allowing the atmosphere to retain more oxygen. According to recent estimates, the partial pressure of oxygen then surpassed 1% of our current level, a determining threshold in the history of life's evolution on Earth. This oxygen threshold is crucial because the more oxygen the air contains, the more organisms can activate efficient metabolic pathways. Eukaryotic cells, equipped with a nucleus, use oxygen to efficiently produce their energy. As concentration increases, ecosystems gain complexity. Multicellular creatures in particular often need a high oxygen rate to ensure gas exchange and maintain their biological activity. After the ice melt, the burial of organic matter in marine sediments and the intensification of pyritization contributed to a significant rise in atmospheric oxygen. At the surface, microscopic algae fed by sunlight proliferate and then sink after dying. Buried beneath the sediments, they escape decomposition, trapping carbon. In depth, sulfate-reducing bacteria produce pyrite, altering the sulfur balance in the oceans. Gradually, this dynamic fosters a sustainable increase in oxygen content. At the same time, a second phenomenon reinforces this dynamic: the emergence of a nitrogen cycle in an oxygenated environment. In this new context, the ammonia present in water is transformed into nitrate thanks to oxygen. This now more abundant compound plays a key role in the growth of many marine organisms, like some algae and animals. They use it to make proteins and other molecules vital to their development. Before this post-glacial period, ecosystems lacked nitrate because nitrogen oxidation required a stable oxygen supply. As a result, primary production in the oceans remained limited, with many biological reactions running slowly. But with increasing atmospheric oxygen, favored by carbon burial and pyritization, ammonium could be converted into nitrate. Specialized bacteria then thrived, fueling new circuits of oxidized nitrogen. These chemical upheavals transformed the biosphere. With oxygen and nitrate now more abundant, microalgae, bacteria, and the earliest forms of multicellular fauna found ideal conditions to thrive. The food chain was enriched and species diversified, and as the seas were no longer frozen by ice, light penetrated further, boosting photosynthesis and increasing oxygen production. After a long glacial era, the Earth changed radically. Temperatures climbed, ice retreated, and vast oceans were freed. In this transformed world, multicellular life took a turning point. Organisms that survived the extremes developed unique capabilities, forged by cold and scarcity. This severe selection prepared the emergence of more robust and ingenious species. When the ice recedes, the climate warms and triggers significant chemical upheavals in the oceans. Erosion massively releases nutrients like phosphorus, iron, or molybdenum, essential for cellular development. Algae and eukaryotes take advantage of this to build more elaborate structures, favoring growth and diversification. This marks a turning point for multicellular life. Meanwhile, microbial mats, survivors of glaciations, continue to produce oxygen and enrich the environment with vital compounds, thus contributing to the rise of new ecosystems. Natural selection was critical during glacial periods. Only organisms capable of surviving extreme cold, lack of light, and food scarcity persisted. Once the ice retreated, these robust species quickly colonized new environments. Some eukaryotic lineages retained traits that made them resistant to abrupt climate variations, ensuring their reproduction in a still unstable world. Even as temperatures rise, this endurance remains an asset in the face of potential future upheavals. The enrichment of oceans with iron, phosphorus, and molybdenum promotes the proliferation of plankton, an essential base of marine food chains. These nutrients, once trapped under the ice, now feed a denser biological network. Thanks to this abundance, more specialized organisms emerge, feeding on these tiny producers. New relationships between prey and predators develop, triggering rapid co-evolution. This dynamism lays the foundations of a more complex, diversified, and stable marine ecosystem. Among the first biological innovations of this era are probably spongy animals, ancestors of modern sponges. Although they have no organs or nervous system, these multicellular beings develop a simple structure capable of filtering water to feed. Through a cooperative cellular network, they manage to maintain their shape and extract necessary nutrients. By colonizing shallow marine platforms, bathed in light and rich in organic matter from photosynthesis, these primitive sponges find a favorable environment for their expansion and diversification. In this new post-glacial environment, the photosynthetic activity of algae and cyanobacteria increases significantly, enriching the waters with oxygen. During glaciations, this vital gas does not completely disappear, but remains limited to thin layers near the surface. With the retreat of the ice, it diffuses more thoroughly in the ocean, making possible the appearance of more complex organisms. Sponges, though elementary, take advantage of this abundance to develop a more efficient metabolism than simple cells. This surplus oxygen thus becomes a key lever in the evolution of multicellular life. About 580 million years ago, Earth was emerging from one of the most rigorous glacial cycles, the gas years glaciation. Less extensive than the large Sturtian or Marinoan glaciations, it nonetheless covered almost the entire globe with ice, freezing the oceans and plunging the climate below 0 degrees C or 32 degrees. The landscape was uniform, white, desert-like, almost devoid of vegetation. Only a few pockets of life survived, nestled in ice-free coastal areas or near still active oceanic ridges. It was in this inhospitable setting that flora and fauna had to find unprecedented survival strategies. Although brief on a geological scale, the gas years glaciation profoundly impacted the Earth. As it melted, the ice caps released immense volumes of water, fueling powerful rivers laden with sediments. These rivers shaped new habitats conducive to life. In the spared wetland areas, cyanobacteria and algae adapted to the cold, filtered light through the ice. In the water, fragile marine organisms found refuge on nutrient-rich seabeds. Every liquid pocket, however small, became a precious sanctuary of life, fragile but active. As the climate warmed, the ice cap receded, first around the equator, then towards the mid-latitudes. The liberated coasts revealed humid plains shaped by erosion. This retreat of the ice triggered a genuine ecological rebound. Sunlight penetrated the oceans more freely, stimulating photosynthetic algae and the return of numerous marine species. The meltwater, rich in nutrients from weathered rocks, nourished the entire food chain, reviving marine ecosystems with unprecedented vigor. In this context of warming and the progressive retreat of ice, multicellular life enters a new era. Paleontologists have noted a striking coincidence between the end of the gas years glaciation and the emergence of the first Ediacaran fossils. Discovered in Australia, these organisms with varied shapes, discs, fronds, segments, represent the oldest known complex beings to date. Their appearance marks a decisive step in the evolution of marine life. The end of the gas years glaciation profoundly influenced the reorganization of life. By releasing surface waters, it enriched coastal areas with nutrients, promoting the emergence of more complex organisms. The Ediacaran fossils illustrate this spectacular renewal, made possible by the combination of warming, massive erosion, and the return of sunlight. This unique context strongly stimulated biological diversification on a planetary scale. At that time, terrestrial flora was almost non-existent, with the first plants appearing much later. However, the shallow waters welcomed microbial mats where bacteria and algae thrived, testifying to the resilience of life in the face of extreme climates. Some species developed pigments to protect themselves from intense rays or optimize their photosynthesis in turbid waters. It was a period of remarkable adaptation. The end of the Snowball Earth era is associated with the gradual retreat of the immense glaciers that had covered almost the entire planet. During the Neoproterozoic, some researchers proposed a less extreme vision than that of a completely frozen Earth, the slush ball hypothesis. According to this scenario, the planet was largely covered in ice, but a free oceanic band remained near the equator. This liquid water zone would have allowed life to persist, unlike a completely frozen Earth. The term slush ball, meaning melting snowball, evokes a planet mixing ice and open sea. This hypothesis is based on various data: paleo-environmental observations, paleomagnetic measurements, and geochemical indicators. These are elements that continue to fuel a passionate scientific debate today. In this vision, the ice-free equatorial band would have been vital for the survival of primitive life. Without it, light would not have reached the ocean's surface layers, making oxygen production almost impossible. Thanks to this opening, microalgae and cyanobacteria would have continued to thrive in illuminated waters. Additionally, chemotrophic organisms could develop around hydrothermal vents, but access to open-air facilitated gas exchanges and nutrient renewal. The fauna remained simple, consisting of rudimentary multicellular forms, but benefited from a more favorable environment. For some researchers, this slush ball would have provided a true lifeline for the biosphere. To support this hypothesis, several studies have simulated a climate with significant temperature differences between the poles and the equator. These models suggest that a band of open water near the equator, darker than ice, would absorb solar energy better, limiting the cooling effect of the albedo. To maintain this liquid ribbon, however, greenhouse gases like carbon dioxide would need to remain present in minimal quantities. This scenario therefore rests on a fragile balance between climate feedbacks, continental positioning, and the chemical alteration of rocks, a process that, depending on the case, can release or consume carbon dioxide. The debate is largely fueled by diamictites, glacial rocks that preserve an equatorial paleomagnetic signal. This suggests that thick layers of ice could have extended to the tropics, reinforcing the idea of a completely frozen Earth. However, some researchers remind us that these data can be influenced by tectonic shifts or variations in the Earth's axial tilt. Other uncertainties remain: subsequent alterations of the rock, errors in the original horizontal markers, or mixes of sediments of different ages. These limitations make it difficult to reach a definitive conclusion on the true extent of the glaciation. The debate between the integral and slush ball model thus remains open. Another clue for estimating the extent of ice relies on the oxygen isotope ratio, known as delta-18 oxygen. This ratio between oxygen-16 and oxygen-18 varies according to the ocean's temperature and the mass of ice present. During major glaciations, oxygen-16 is more trapped in the ice caps, enriching the oceans with oxygen-18. The carbonates formed in these waters retain this imprint. Thus, high values of oxygen-18 in ancient rocks reveal intense glaciation, possibly reaching the equator. However, some data also show a slight rise in temperatures, suggesting that a narrow oceanic band might have remained liquid. The analysis of oxygen isotopes offers a valuable window into the climate hundreds of millions of years ago. These data allow the reconstruction of a complex climate puzzle, but their interpretation remains delicate. It is necessary to take into account the transformations undergone by sediments after they are deposited, a process called diagenesis. Each rock sample, each outcrop or fossil formation adds a piece to the whole, helping to better grasp the actual extent of ancient ice sheets. Thus, the slush ball hypothesis evokes a world less frozen than previously thought, where a band of ice-free ocean around the equator might have allowed microscopic life to persist through photosynthesis and chemosynthesis. Despite geological evidence suggesting extreme glaciation, the existence of this liquid zone remains conceivable. The debate, still active, revolves around subtle details: ice thickness, continental arrangement, climate feedbacks. Nothing yet allows for a definitive resolution. Analyses are becoming more precise, and each new piece of data brings us a little closer to the truth about this extraordinary era in Earth's history. We enter a key phase of the Neoproterozoic, where tectonics begin to dictate the destiny of carbon dioxide in the long term. After the great glaciations, thick carbonate deposits form, storing carbon sustainably. Slowly, tectonic plates carry these deposits into subduction zones, burying this gas for millions of years. This natural trapping limits climate warming, but this same process also feeds deep magma chambers. Sometimes it triggers gigantic volcanic eruptions, suddenly releasing CO2 and sulfur dioxide into the atmosphere, thereby reactivating large-scale climate cycles. If carbonate subduction helps remove carbon dioxide from the atmosphere, it can also cause its abrupt release during major volcanic eruptions. This is where the silicate thermostat comes into play, a natural climate regulation mechanism operating over millions of years. When silicate rocks of the continental crust react with rainwater charged with CO2, they release ions that, at sea, transform into carbonates. The higher the atmospheric CO2, the faster this process accelerates. Conversely, if CO2 decreases, erosion slows down. This chemical cycle acts as a self-regulating valve, stabilizing Earth's climate over the very long term. The dynamics initiated in the Neoproterozoic continued throughout the Phanerozoic, marking a turning point in the geochemical evolution of the planet. The ongoing subduction of carbonates formed during the great Sturtian-Marinoan glaciations has durably trapped carbon dioxide deep underground, slowing its return to the atmosphere, except during orogenies or major eruptions. This prolonged storage has contributed to a sustained global cooling. Meanwhile, the gradual decline in volcanic emissions has kept temperatures at a moderate level, favoring a rise in oxygen. Consequently, photosynthetic and aerobic organisms have multiplied, paving the way for more diverse, stable, and complex ecosystems. But this natural regulation remains fragile. Subduction can sometimes increase pressure in zones of partial melting, triggering vast basaltic supereruptions. True lava fountains, they suddenly release enormous amounts of gases, including carbon dioxide. If these emissions exceed the weathering capacities of silicate rocks, they cause a temporary warming. Over several millennia, the biosphere must adapt to these upheavals, affecting food chains and plant growth. However, it is precisely the alternation between deep burial and volcanic release that ensures the resilience of our planet. Life depends on these oscillations in the carbon cycle, between relative stability and occasional crises. The climatic balance we know today has its roots in the mechanisms put in place as early as the Neoproterozoic. Since then, tectonic plates continue to drag ancient carbonates into subduction, facilitating the long-term sequestration of carbon dioxide. Meanwhile, volcanic emissions maintain a regular supply of gases into the atmosphere. Over the long term, the silicate thermostat thus ensures relative stability, conducive to the evolution of life. The gradual enrichment in oxygen has allowed us to exceed 4% partial pressure, paving the way for more complex life forms. Between eruptions and erosion, Earth adjusts its balances, sculpting a world where biodiversity can renew itself without falling into extremes.